Hi, this is the Science Chef. In this video, we'll be learning about the concept of isotopy with common examples of isotopes and their uses. Don't leave this channel, and we'll be back after this timeout. John Dalton, in his atomic theory, postulated that all the atoms of an element are exactly alike in all ramifications and different from the atoms of other elements. However, this postulate, like three other postulates of that theory, was faulted with the discovery of isotopy. So, what is isotopy and why did its discovery question the correctness of Dalton's atomic theory? Isotopy is the existence of two or more atoms of an element with the same atomic number but different mass numbers. Atoms that exhibit isotopy are called isotopes. Therefore, we can define isotopes as atoms of the same element that have the same atomic number but different mass numbers. From these definitions, it is important to note that isotopy is a phenomenon, while isotopes are atoms. The difference in their mass numbers is due to their different number of neutrons, as we will see in our examples. Let's look at some important facts about isotopes. 1. Isotopes have the same number of protons and electrons, but different number of neutrons. This explains why they are atoms of the same element, because it is the proton's number or atomic number that defines an element and not its mass number. For example, the atomic number of oxygen is 8, while that of fluorine is 9. So if the atomic number of an atom changes from 8 to 9 in a nuclear reaction, it means the oxygen atom has been destroyed, while the fluorine atom has been created. However, calcium and argon both have atoms with mass numbers of 40, but because their numbers of protons are not the same, 20 for calcium and 18 for argon, they cannot be said to be atoms of the same element. 2. Isotopes exhibit the same chemical properties but different physical properties. This is because the number of valence electrons determine the chemical properties of an element, while the mass number determines its physical properties. Therefore, since isotopes are neutral atoms with equal numbers of protons and electrons, they will exhibit the same chemical properties. 3. The proportion of an isotope present in a given sample of an element is known as its relative abundance. Relative abundance can be expressed as percentage, ratio, or decimal. When expressed as a percentage, the sum of the relative abundances of the isotopes is 100%, and when expressed as a ratio, the total relative abundances add up to 1. 4 and the last. All elements exhibit isotopy. This explains why their relative atomic masses are not whole numbers. This is because it is a weighted average of the mass numbers of their isotopes. Even though all elements are made up of isotopic mixtures, in this video, we'll focus on the common examples of elements that exhibit isotopy, starting with hydrogen. Hydrogen has 3 isotopes, namely hydrogen 1, also called protium, hydrogen 2, called deuterium, and hydrogen 3, also known as tritium. Hydrogen 1, which is commonly regarded as ordinary hydrogen, is the most stable with a relative abundance of about 99.98%, followed by deuterium with an abundance of about 0.02%. Tritium is radioactive and is rarely found in ordinary hydrogen. It has a half-life of about 12.3 years. Half-life is the time it would take a substance to decompose to half its original mass or concentration. Half-life is not within the focus of this tutorial. We will treat it in more details in another tutorial. Just hit the subscribe and notification buttons to stay notified whenever the video is published. As we can see, hydrogen is the only element whose isotopes have names that are in common use today. Deuterium is represented as capital D, while tritium is represented as capital T. But for consistency's sake, hydrogen 2 and hydrogen 3 are commonly used. Ordinary hydrogen contains only one proton and one electron with no neutron. It is the only atom with an incomplete set of subatomic particles. Deuterium, on the other hand, is made up of one proton, one electron, and one neutron, while tritium contains one proton, one electron, and two neutrons. The next example we'll be considering is carbon. Carbon has three isotopes, which are carbon 12, carbon 13, and carbon 14. The first two are stable and have a relative abundance of 98.9% and 1.1%, while the carbon 14 is radioactive or a radioisotope and is used in archaeology to determine the age of organic fossils. It has a half-life of about 5,730 years. Carbon 12 has 6 protons, 6 electrons, and 6 neutrons, and carbon 13 has 6 protons, 6 electrons, and 7 neutrons. Carbon 14 also contains 6 protons and 6 electrons, but has 8 neutrons. Next is oxygen. Oxygen has 3 isotopes, namely oxygen 16, oxygen 17, and oxygen 18. Oxygen 16 is the most stable and has a relative abundance of about 99.8%. Oxygen 17 and 18 are radioactive and have relative abundances of about 0.04% and 0.2% respectively. Oxygen 16 contains an equal number of protons, electrons, and neutrons, while oxygen 17 and 18 contain 9 and 10 neutrons respectively, in addition to their 8 protons and 8 electrons. Finally, let's look at the isotopes of chlorine. Chlorine has 2 stable isotopes, chlorine 35 and chlorine 37, with the relative abundances of 75% and 25% respectively. This means that in every 100 atoms of a chlorine sample, 75 atoms will be chlorine 35, while 25 atoms will be chlorine 37. Chlorine 35 contains 17 protons, 17 electrons, and 18 neutrons, while chlorine 37 contains 17 protons, 17 electrons, and 20 neutrons. Apart from the ones we have discussed already, let's look at other common uses of some isotopes. In medicine, iodine-131 is used to treat cancer of the thyroid gland. Cobalt-60 is used for destroying the growth of cancerous cells in radiotherapy. Phosphorus-32 is used for treating leukemia and cancer of the skin. Carbon-14 is also used in a breath test to detect the ulcer-causing bacteria Heliobacter pylori. Iron-59 is used for anemia diagnosis, and gold-198 is used for liver disease diagnosis. In the industry, cobalt-60 is used for the rapid checking of faults or cracks in welds and castings. Cesium-137 and cobalt-60 again are used to inhibit the growth of microorganisms on foodstuffs, thereby elongating the shelf life of those products. And finally, deuterium is used for making heavy water used as a coolant in nuclear reactors. In our next tutorial, we'll be learning about isotopes calculations. If you'd like to be notified when the video is published, kindly like this video and subscribe to our channel to encourage us to do more videos like this. Thanks for watching and stay safe till I see you when I'll see you.